Very good afternoon, all. I hope that now my voice will be better, although I had a sore throat, so I could not record the lectures earlier, but I'm feeling better now, so I'm trying to record, and hopefully this is easily, or this is at least clear to you. My voice is coming to you. So we have discussed last time the fast transpose, and I have asked you to do the programming and implement with 4 main steps. I hope all of you have implemented that. Just to help those who have not been completing this coding, I'll show the code also. But before I go to the demonstration, for the step 4, if you remember, we discussed that we need to put the elements of the original matrix into the corresponding transpose matrix. So for that, obviously, we need some loop. I said, yes, I need some loop from I equal to 1, I less than equal to n, I plus plus. And we wanted ultimately the original matrix elements to go into somewhere. Obviously, they have to go into the transposed matrix. So we remember that we wanted something like this to be done. Now, those who could not find that how to implement this step, or probably at this step they might have found some difficulty. So I'm telling you a trick how to solve such problems. First of all, I know that, yes, I want to copy something from original matrix into transpose, this array to this array. Now, like this value of row will be copied into the dot column, and into dot row, the correspondingly original dot column will be copied, and similarly dot val will be copied. Now, but we are not sure how to refer the indexes, etc. So, a systematic process. One of this probably is guaranteedly correlated with the loop variable I. So if you just start thinking that in the original matrix, 1 to n elements are stored, which are the non-zero values of the corresponding sparse matrix. So those are being considered one by one. So I am sure that this index I am able to think that I need here I. So at a time, ith entry is being considered. Now, should it go to transpose matrix also into ith position? Obviously not. So I'm not sure where to go. And this is where my starting index, row comes, etc. All those variables come into picture. So if you are not able to think, okay, let's think that I will use here some variable k, and later, of course, that will be incremented. I will be automatically incremented, so I need not think, but later I will do increment k. Then what should be k? Now, k is the index in the transpose, and it has to be at the position which is found for the corresponding row number. This row number we discussed last time that this is being found, and this information we were able to generate through certain array which we used starting index. So I generated a starting index array. So that is going to be useful to me to generate this k. So I can definitely think that starting index array will be used, and I need something here for getting the k. So k will be the index at which the entry will be stored into transpose, and this entry should come from array in starting index. Now, what should be the value here? Again, I need to have some variable here. Now, what is this? If I remember well, if I can think, good enough. Otherwise, you can assume, fine, I will assume it's some variable m, and then you can think of what will be m. Starting index of which in a particular position? M. What is M? M is going to be the new row number or old column number. So probably now I get the idea that it is nothing but original I dot column number. So from this I am able to get this information. From here, this M comes and reaches there. From there I get k, and then k reaches here. Rest, increment, etc., starting index, etc., all those logics can be planned, but this is how you can develop the step systematically if you are not able to do that in a systematic manner initially. I think there was some disturbance because of this. I have corrected that. So now you can easily see that this is how I did. So I just, because the focus was not clear, so I just quickly reiterate what I did was, we said that, of course, I'm clear that I need a loop for I from something to A1 to N. And I'm also clear that original I dot row dot column and dot val will be stored into some place of a transpose matrix or array dot column dot row and dot val. But this I was not clear, so I assumed that I will use some variable k, and then k, how will I find? I remember that I have discussed to generate one starting index array from where I could get that k easily, and from where or which position of starting index I should use. So I thought, okay, let's assume some m. What should be m? It should be the column number of the original matrix, which will become the new row number. So now this m is coming from original I, and I is already well defined. So this entry is well defined. So I'm able to generate the whole code easily. For further clarity, let me go to the dev.cpp code and demonstrate you the corresponding fast transpose. So here is the corresponding code which is shared with you. Of course, the rest of the code remains same. I have the read transpose, I have the fast transpose or the transpose and then display. So read transpose, which I initially discussed with reading the transpose of a matrix, and then displaying also I have discussed last time for the normal transpose logic. The rest remaining similar. Fast transpose, parameters again remaining same. I can say, okay, total rows, how many total rows or old total rows you could say, that is original 0.row, and they will become now the column numbers, total columns, new total columns. Similarly, total columns earlier, they will become the new total rows, so that also I store, total number of values will remain same. Step 1, I wanted new row terms to be initialized. New row terms means total number of old columns or total number of new rows, those many entries will exist. So I have initialized. Then I wanted the increment of the total number of new row terms. So whatever is the column number available corresponding to that, counter will be incremented. So I found column number from the original I dot column, and corresponding to that entry in new row terms, I incremented. Column number means new row number. So in new row terms, it is incremented. Then I calculate a starting index for the 0 new row number. Obviously, it is 1. For the remaining, it will be generated with the previous starting index and corresponding number of count of elements into the corresponding new row number. So j minus 1 plus new row terms j minus 1, that will generate starting index j. And then final step 4, which I have just discussed. So I said transpose. For a better readability, I use the variable name as, instead of k, I say index in transpose. And this index in transpose will be used to store all 3 values. How to get index in transpose? It will come from starting index new row number, and new row number will be generated from original. And of course that plus plus, because starting index should be incremented, and this is variable k or I, whatever you say, accordingly this code is written. So this is the way I'm going to write my transpose, faster transpose. I hope this is clear and it helps you in doing the better programming. So let me just go back and resume with the next discussions for the today. So having said that, now let's resume here and go for the further programming. So now today we start with some new concepts of programming beyond this matrix, etc. And we will systematically go for the sorting algorithms. So sorting word, all of you are very clear, knowing all that easily, that arrange in, normally we say ascending order, by default ascending order. Of course, it can be adjusted to do it in descending also if needed. So my sorting is arranging the any elements or arranging the array or any other values list, arranging the list in ascending order of their values. So we are going to study a lot of sorting algorithms. I'm sure all of you have probably understood and worked with one simple algorithm, which is bubble sort. You have done probably last semester and probably understood well. But there are much more standardized and good algorithms available. Each have its own advantages and some disadvantages. So we are going to study one by one many of them. For today's discussion, we are going to focus on selection sort and insertion sort. And subsequently, we will be talking of the few more algorithms like merge sort and quick sort, etc. Sorry. So let's go one by one. Selection sort. Now, whenever we are going for any standard algorithm, there will be effectively a well-defined methodology, and we must follow that methodology. We should not use a wrong methodology to implement any specific algorithm. Like insertion sort working should not be changed if I'm implementing insertion sort. Similarly, selection sort. So selection sort has a well-defined methodology. What does that say? I will explain in 2 lines, or I'll write the meaning of this selection sort in 2 lines, and then we will discuss everything about this. It says, out of the unsorted list, find the smallest element and place it next in the sorted list. In fact, this 2-line explains everything about the selection sort. I repeat, out of the unsorted list. So initially, my full list will be unsorted, obviously. Slowly, the out of unsorted list elements will keep on going to the sorted part, and unsorted list will keep on reducing. It says find the smallest. Instead of find, you can think to use the word select. That is why it is called as a selection sort. So we are selecting the smallest and place it next in the sorted list. Initially, sorted list was empty, so this will be put next in the sorted list. I will say further that place in this next in the sorted list is equivalent, in case of an array, the above statement is equivalent to saying place it at the start of unsorted list. So I say this is one and the same thing. So my above statement is equivalent to saying, in case of array specifically, that place it at the start of unsorted list. Why do I say? In array, all elements are in the sequential contiguous locations. So if I at any stage, if I say up to this was my sorted list, then obviously my unsorted was just next to that. Out of this, finding the smallest, let's say this element is the smallest. Now, whether you say bring it at the next of the sorted list or bring it at the start of unsorted list is one and the same thing. But this is clear and easy to understand. So now let's go and find out what does this mean. Selection sort explains how it will work. Let's take an example. Let's say I have some data 15, 8, 3, 7, 11, 9, 4, 16, and 10. Let's assume this. Say I have such a list, fully unsorted. So it says out of unsorted list, select the smallest, find the smallest. How to find the smallest? I will start from here. Say this is smallest. Then next I will say, okay, 8 is further. 8 could be smallest. And through this process, I will find the smallest here. 3 is the smallest. 3 should be placed at next in the sorted list. Initially sorted list is empty, or it is equivalent to saying place it at the start of unsorted list. So 3 should come at this position. How to bring? Obviously 15 should not be lost. So I will say interchange these two values. So that will mean 3 will come here, 8 will be already here, 15 coming here, and rest all remaining as it is. But by this process, up to this is a sorted list, and now remaining is unsorted list. Again, same rule, out of unsorted list, find the smallest. Out of unsorted list, find the smallest. This is the smallest, and bring it at the start of unsorted list. This list has 8 here. Of course, these to be interchanged. So 3 was already sorted. 4 also comes, and this becomes a sorted list. 8 goes here, and now my unsorted list is 15, 7, 11, 9, 8, 16, 10. So this becomes unsorted list. Up to this is sorted, and this is unsorted. Similarly, now out of this smallest will be found. 7 will come here, 7 will come here, 15 will come here. Out of remaining, smallest will be found, 8 will be found. So 8 will come here, 15 will go here. After this, out of unsorted list, this side, smallest will be found, 9. So 9 will come here, 11 will go here. Out of this unsorted list, 10 will be found, 10 will come here, 11 will go here, and so and so. So this is the way my selection sort will work. I hope it is easy to understand. Now, how to do coding for this? So, knowing this logic, you should be able to do coding. I say consider unsorted list, because my whole logic remains on unsorted list and finding minimum from there. So let's assume unsorted list is from some position array I to array n minus 1. Guaranteedly n minus 1, because my array always starts from 0 to n minus 1. My right side list will be always unsorted. So I can always say that guaranteedly it is one and the same thing. So I say unsorted list size will keep on changing from the left side. So I say let it start from I onwards, goes up to n minus 1. Now, obviously, I can know from where I will start and slowly how I will change. But I will say, what is my aim? Find the smallest out of ARRI to ARRN minus 1. And once you find, that will be, let's say, some step 1. Then what I will do, this smallest, bring the smallest at starting position. What is starting position? Effectively array double I. That will effectively be equivalent to some interchange or swap to be done. So this is my whole programming, and this process to be repeated. So I will need a loop of I to change. From where I should start? Obviously, I can say first time unsorted list starts with I as 0. 0 to n minus 1 is fully unsorted. Next time, one element will become sorted and so and so. So I have to decide where to stop. So I equal to 0 will be the starting point. What will be the final step? Of course, one step you could easily say is something related to n minus 1 or something similar to that. So I can say you can even write less than or less than equal to n minus 1 or something like that. You have to think of. The only point which I'll extra add is that at the end, if unsorted list has only one element, there is no further need to do anything. One element is guaranteedly the correct value. So once we reach to the n minus 1th element and smallest list, or my unsorted list has only one element, that will be obviously the largest out of the total elements, and that has reached to the last position. Having said that, so I can easily see that my logic will be something like I equal to 0, I less than or something, whatever you want to write, I plus plus, and effectively I have to consider list array I to array n minus 1 and find smallest out of this. Step 1. How to find smallest? So normally whenever I have a list and find the smallest, simplest logic which you could think is that consider the first value itself to be the smallest and then keep on comparing with the remaining values, and whenever you find a smaller than this, update your smallest element and proceed towards the end. Once you keep on comparing, you will reach to the end. Having said that, let's see a partial code which will help you in doing simple programming. So I'll say, okay, selection sort. First of all, of course, I will have ARR main bait. Whether you make it as int or not is your choice, not necessary for the time being. Yeah, this also you might make a function prototype. I have already discussed sometimes in the class also that why do we need this. Read the elements, read n and total array being read. So ideally this must be the correspondingly indented code. So I have done this, and then I'll say fine, selection sort. What is more important? This function. It can be int or void. Probably I'll take it void, not going unnecessarily into any other detail. So let it make it void. And array and end pass. So I say, yes, this is going to be the condition, I equal to 0. Less than equal to n minus 1 also can be written. Nothing wrong with that, but probably I say even not needed, because when I reaches to n minus 2, up to that is fine. After that, only one element will be left, nothing to bother. So here I say now, assume the first element to be the smallest. Keep on comparing with next element onwards up to n minus 1. So whether you write less than n or you write less than equal to n minus 1 is one and the same thing. And then you compare your current element. If that is lesser than this, you should update. Finally, the found smallest element of the array should be interchanged with which index. So now you know well that it is going to be probably this one. Having said that, probably this is what I will give you, fill in the blank, and you should try to complete the code. Of course, next time we will show what is a complete code. If needed, you are not able to make it. Resuming further, let's go to the next logic. Then similarly, we go to the next algorithm, which we call as insertion sort. So just now we discussed selection sort and understood its a basic working based on 1 or 2 line definition. Same is the case now also. We have a 2-liner definition for the insertion sort. So it says, out of the unsorted list, take the first value, first element. So I'm not considering the whole list. I'm taking the first element of the unsorted list and insert it at the right place, at the proper place in the sorted list. This word insert needs to be properly understood. I say insertion sort is exactly easy to understand if we remember how do we arrange cards while playing. Whenever we are playing the cards or Uno game, we have a tendency of keeping the cards in my hand in a particular way. This is effectively nothing but insertion sort. What do we do? Let's recall. If I'm playing cards, some of you might not be playing, so don't bother, but you must be playing Uno or similar game. And it's a tendency that we keep the cards in our hand in a particular increasing order or sequentially arranged order. Let's assume I have some cards in my hand, and I have cards in my hand as, let's say, 5, 8, 11, and 12. And these cards are already in my hand. So I have 4 cards in my hand. And now I get a card numbered with 7 coming next. So I pick up a new card, and the new card being picked up is a 7. What do I do? Normally, all players have a tendency not to keep 7 randomly anywhere, but what they will do is insert the card at this place. That's what insertion word means. Of course, in hands playing, you could insert the card by creating a place in between. In case of an array, there will be no insertion directly possible because you can't put the value in between without creating a place in an array. So this effectively will mean, what did I do really? I had these cards. How did I arrange? How did I place my 7? Was one way I could compare either from the left side and then finding a place for 7, or compare from the right side. For programming purposes, comparing from the right side will be much more meaningful and useful because we have to create a place, a space. Left side is already at index 0. It cannot be further shifted to left. So we will always aim to have insertion done or comparison done from the last position. So I say, when I have 7 to be inserted, what do? I compare it with 12 and find that a 12 is bigger. So that means 7 has to come on the left of 7. 7 has to come somewhere on the left of 12. Might be further left, but definitely on the left of 12 means 12 should shift by one place and create a space which could be used anytime later. So as soon as I find that 7 is lesser than 12, what I do is shift 12 and create a space. Then I come to next element, 11. 11 is also bigger, 7 is lesser than 11. So I will say, okay, 11 also to be shifted. So 12 shifted, 11 shifted. Then I further compare with 8. 8 also I find 8 is bigger, so 8 also shifted. And then I come and compare with 5. Now I find right place available. 5 is lesser, so 7 has found its position. 7 is put at this place, and this place because is already available because I have shifted 3 elements. So now my array or my cards in my hand are in this order. 5, 7, 8, 11, 12, 0 to 4. Let's say a new card comes out to be now 2. Again, the same process. First of all, I will compare 12 versus 2. 12 will shift, 11 versus 2. 11 will shift. So now I am getting my array. Of course, this is index 5. This is index 4. So at 4 earlier it was 12. Now 11 will come. Similarly, now 8 will be again shifted. 8 versus 2 comparison. 2 is the new value or new card. 8 also shifted. 7 is also bigger than 2. So 7 also shifted. 7 comes here. Everyone is getting shifted. 5 versus 2. 5 also shifted. Now, once you have reached to 0th index and that is also shifted, no further comparison needed. This point has to be stopped. No further comparison. And automatically 2 will be inserted here. So now I have my elements as 2, 5, 7, 8, 11, 12. Say now I want to insert 30. New value. 13 to be inserted. First itself comparison. 13, 12 is not greater than 13. 12 shifting not needed. It will mean 13 is already correct. It can be here. So this is what we mean by inserting at its proper place. So this is what we mean by insertion sort. Now, what we did, out of unsorted list, take the first element. So till now we discussed in terms of a cards. Now let's talk in terms of an array. Say I have an array, and in the array, effectively I have, let's say, original list. Let's go to the next page and I'll explain it everything there. I'll take the same data which we took for the selection sort. So we assumed data to be 15, 8, 3, 7, 11, 9, 4, 16, 10. This is my total list. Always consider list in terms of course, this is index 0 and this is index onwards. 0, 1, 2, 3, 4, 5, 6, 7, 8. 0 to 8, total 9 elements. Now, consider the list as a 2 parts. One is a sorted list, one is unsorted list. Which one is unsorted? The whole list is unsorted. I say, but now it says you have something as a sorted. So I can say, safely I can say, up to this list is already sorted. One element taken, list is already sorted. Or I will say, in general, at any stage, if you assume that this up to this, the list is sorted, then of course 8 can be inserted. For example, at some stage, if I have, let's say 3, 7, 8, 9, this one as sorted, and now you are trying to insert some new value, so already sorted list was considered and shifting could happen. So I can say safely, this is sorted and other list is unsorted. So that will mean my unsorted list is always from ARRI to ARRN minus 1. This is totally unsorted list. But when I say sorted list, now I could say I up to, so effectively it means array 0 to array I minus 1 is a sorted list at all stages. So to start with, I could be 1 onwards because array 0 I can consider for the time being sorted. Out of unsorted list, I will take one element only. Take the first element, definition simple. Now recall, in case of a selection sort, I needed the whole unsorted list. Initially, sorted list was empty because smallest element was to be found. Here I can say up to this list is correct and I'm going to insert in the sorted list, so I can safely assume first element is okay, rest will come in between. So in selection sort, I traversed the whole unsorted list and found the smallest. In case of insertion sort, I will not be traversing the unsorted list. I will take only one element out of unsorted list, that also the starting element, and sorted list will be traversed in the reverse direction. Just see what happened. 15 is already considered as a sorted at index 0, and 8 is the new element coming up. 8. So I will take a new variable, new val, where I will store 8 and keep on comparing. Why I'm taking a new variable? Because this space I will be utilizing for shifting my elements if needed. And 8 should not get overwritten at any stage, obviously. So I will compare 8 from in the sorted list backwards. Compare 8, compare this new val 8, not this 8, I'll say this new val 8 versus 15. 15 is bigger, 15 needs a shifting. So 15 will come just to the next position. So now just see what happened. This was index 0. This is index 1. 15 will be copied here. And I will not lose anything. I claim that this position was guaranteedly free because 8 I have stored somewhere and I'm not losing anything. 15 I brought here. This place is empty. And because we have already reached to 0th index, nothing further to be done. Initially 15 was written here. Now this 8 will be written here. This is a sorted list. Next time, sorted list is 8 and 15, and a new element being considered is 3. So first of the unsorted list, out of the total unsorted list, take the first unsorted. 3 is unsorted. I will take new val variable, store 3 here. You can again see why this is helpful to me. 3 is actually stored at index 2, and that gives me a place for the shifting also. So 3 versus 15 obviously will mean shifting could be done. 15 is bigger, so this 3 will be overwritten by 15. 3 versus 8, 8 is bigger, so this 15 will be overwritten by 8, and we have reached to the last position, so 3 will be coming here. So now my array has become 3, 8, 15, 0 to 2. Take the next unsorted element, first element, 7. 7 will be considered, which is at index 3. New val variable taken, 7. So 7 will be now considered. 7 versus 15 comparison. 15 needs a shifting. 15 copied to the next position. 8, 7 comparison. 8 needs shifting. 8 comes here. 7 versus 3. 3 is obviously smaller, so 7 has found its place. As soon as you found its place, I need not go further. So I get 3, 7, 8, 50. Now you will understand one more important point. Next time I am going to compare with 11. New val variable 11. 11 to be inserted at its right place. How? 11 versus 15. So it means this place gets overwritten by 15. 0, 1, 2, 3, and 4, obviously. 11 versus 8. 8 is a smaller. As soon as a smaller, I say need not compare at all backwards. So I started comparing backwards, but as soon as the element which was found to be smaller in the sorted list, I will stop. And I can easily say no further comparison needed. So, of course, now I can make the logic from based on this. So let's do the coding part. My logic is simple. I said, consider ARRI to n ARRI n minus 1 is unsorted list. That automatically means I will need a loop for I because I should change. My unsorted list will keep on decreasing. Initially, I can safely start to say I equal to 1 because I 0 means one element only. So I will say array 0 to array I minus 1 is a sorted list. So initially there can be only one element which will be considered as a sorted list. So I can say my first time I will be 1 and of course up to the last element I will go. So less than equal to n minus 1 or you say less than n, 1 and the same thing. Effectively what I have to do, first element of unsorted list to be inserted. Which is first element? ARRI. To be inserted. Where? To be inserted in sorted list, which is array I minus 1 and down up to 0. I have to go backwards. So effectively from I minus 1 backwards I have to go. So I'll take some variable, let's say j equal to I minus 1. And I have to keep on shifting some element based on some condition. But I can easily see that shifting of how many elements needed was dependent how many times I compared and whether all of them needed shifting or some of them. So for loop was not suitable because how many times shifting will be needed is not fixed. It is dependent on the condition. Hence, my while loop could be condition, which could be useful. Loop I need because I have to do some shifting. How to shift? Ultimately, I needed shifting. Internal step, what I said, that if I'm talking of comparing 15 with 11, 15 will go one place right. 15 is at index j. J is this one. So effectively, what I need is ARRJ plus 1 to get ARRJ. ARRJ is, for example, in the last case 15, and 15 will be shifted to just next position. And just next position is guaranteedly free. So before that, I must have taken some new variable val, which I wanted ARRI to be inserted. So this is inserted. This value has been saved in new variable, new val, and now that location is free. So my any element might require a shifting to the next position based on some condition and then maybe some increment, etc. Once you come out, the necessary shifting has been done. So I have to place my element new val at some place. Now, what is this index? Of course, this index will be in terms of j somewhere. It could be j, it could be j minus 1, it could be j plus 1, something like that, because j was the address where my loop will terminate. J was the point which decided no further comparison needed, element's position found. So based on that, you have to think of through an example that whether I need j or j minus 1 or j plus 1, etc. Having said that, I'll show the partial code and then I will stop discussions on this. So let me show you the partial code. Of course, before seeing the partial code, I will suggest you to try to pause this video and try to write code of your own based on the discussions which I have just shown. So based on this code, you should be able to write most of the code. But if you need further assistance, then you should just see the video and have the partial code shown. I still say there is no need to see the partial code. You can easily make that. But those who want to see, for them I'm showing the partial code. So my function will remain again very similar. I can easily say let it be also void. Function name will change, rest everything will remain same. I say first time I will start with I equal to, we already discussed, maybe 1, less than equal to n minus 1, etc. New val to be inserted from where, from I minus 1 backwards to go. Loop here, which is obviously some kind of a while loop. And array to be copying the element to the next right position. Any element which needs shifting by one place will go to the next position. And then obviously I need a new val to be inserted here. Having said that, I think it's good time to give you thinking time and try to apply your logics and implement this. With this, I think I must stop here. So homework is obvious. I think you all well can now easily aim to do. Implement both programs, selection sort as well as insertion sort. Of course, if you are not able to do, next PPT will help, your next video will help you in understanding that. But based on the today's discussion, you should be able to do that. And that is what programming is all about. You are not supposed to see the code and understand its working. You are supposed to understand the logic or basic concept of that particular program and develop or write your own code. I insist again, write your own code and then you will become a good programmer. Bye-bye. All the best to all of you. Let's